Hello everyone, this is Zhibo Yang. Today I'm going to present our work on hierarchical proxy-based loss for deep metric learning. In computer vision, metric learning seeks to learn a function that measures the semantic similarity between image pairs, and it is very important for the learn the similarity function to be able to generalize to unseen classes. However, existing proxy-based losses focus on learning a discriminative representation, ignoring the class-shared information and the implicit data hierarchy. This could harm the generalizability of the learned metric to unseen classes. Given a set of training samples, traditional proxy-based losses usually create a learnable embedding vector for each class as proxy. During training, images are pulled to the corresponding proxies, while pushing away from the proxies from the different classes. In the ideal scenario, after training, we will have an embedding space with a large between-class margin and small within-class variance. Hence, the distance between class 2 and 3 could be larger than the distance between 2 and 4. However, real-world data often has implicit hierarchies. For example, class 1 to 3 might belong to one supercategories, while class 4 to 6 belong to another. Naturally, we would prefer the samples within the same supercategories to be closer to each other, but this is often violated by traditional proxy-based methods. So to address these problems, we propose a hierarchical proxy-based loss that captures both class discriminative features and class-shared characteristics without breaking the implicit data hierarchy. In order to preserve the data hierarchy in our embedding space, we not only want good between-class separation, but also large margin between supercategories. There are two major benefits of learning such a hierarchical space. First, it benefits the real-world data, which are often organized in a hierarchical way. Second, we can preserve useful features shared across classes through the supercategories. Here is how we approach it. To illustrate, let's consider a simple two-level hierarchy. Suppose we are given a dataset of 6 classes. Like traditional proxy-based methods, we first create a fine proxy for each class and try to pull samples close to their proxies and push away the samples from the proxies of a different class. For the cost proxies, we perform a similar procedure. Finally, our hierarchical proxy-based loss is a weighted combination of the traditional proxy-based loss at every level of the hierarchy, and it can work with any existing proxy-based loss. Now the problem is, how do we obtain the hierarchy? One simple way is to directly use the ground truth hierarchy if available. However, most datasets do not have those annotations. To address this problem, we propose to learn the hierarchy using online clustering. Our online clustering algorithm works as follows. First, we perform clustering on the fine proxies to obtain the initial cost proxies. Then we apply our hierarchical proxy loss to update the embedding network and the fine proxies. And for every k iterations, we update the proxy assignment by reassigning each fine proxy to its nearest cost proxy. Then, according to this assignment, we set the cost proxies to be the center of the corresponding fine proxies. We repeat step 2 and 3 until convergence. To measure the performance, we use a more standardized evaluation protocol. One can see that our method consistently improves the proxy NCA and the proxy anchor loss. And our hierarchical proxy anchor loss achieves the state-of-the-art performance compared to all other methods. Similar results can be observed under the traditional evaluation setting as well. Here we'll visualize some image retrieval results where the red box indicates the false positive. It is obvious that our hierarchical proxy loss is better than traditional proxy NCA in both accuracy and the overall quality of the image retrieval results. In this slide, we visualize the learned embedding space using t-SNE. As highlighted in the red boxes, our method tends to group similar categories into a larger cluster while still remaining good separability between classes. So as a summary, we showed that our hierarchical proxy loss improves the standard proxy-based losses by leveraging the class-shared information and the implicit data hierarchy. This helps the generalization to unseen classes. In this work, we only experimented with a simple two-level hierarchical structure. In the future, we plan to explore more sophisticated configurations of our method. Thank you for listening.